This is a talk about async sequences and the algorithms that you would use to compose them. I'm Kirk Shoop. I work for a subsidiary of Microsoft called Microsoft Open Technologies, and we do open source on behalf of Microsoft. I'm a dev. I contribute to various open source projects. This is something I've spent the last year and a half doing nights, weekends, basically stealing from family life because I just fell in love with it. What you're seeing here at the bottom is rxcpp using a port of my demo to use SDL compiled within Scripton and running in the web page. So this is JavaScript compiled from C++. It's kind of fun, and it follows the mouse. So, I'll start with a couple of contrasts. This is concurrency. You got a whole bunch of things that are independently eating. None of them are coordinating. They just, as fast as they can, each of the workers, all of your resources are being used at the same time, and you're just as eagerly and as fast as possible trying to get a whole bunch of stuff done. And all the stuff that you want to get done is right there in front of you. You're not waiting for it. Async is more the lazy approach. You just kind of want to sit back and wait for the fish to bite without doing any effort until it does. Because it isn't there yet, and you want to use the minimal resources possible waiting for this thing to come in that you need to then go do some work with. Just because you've got this lazy sequence of things, that fishing line also kind of demonstrated that things come one at a time. Even though you have this serial line, you can put multiple lines in the water, or you can have multiple streams shooting things. And so concurrency comes when you have more than one of these streams going at a time rather than within one stream. And streams aren't always bytes. It concerns me a bit when I see so many different ways to deal with these different async values over time. I've got events for UI, and I've got streams for bytes on from a file, and I've got we keep inventing more and more representations of what is essentially just a stream of things coming in over time. And when you have that many representations, you have problems with algorithms, because you have to re-implement all your algorithms for all your representations or build adaptions between all your representations. So this is all about the algorithms, not the representations. I think it's important to pick one. That would be great. But it's really the properties of the representation that will matter. I'm going to be showing one, which is rxcpp. But the important thing is to have an algorithm set, just like we have for sequences in the STL, and we will have for ranges in the STL, that lets you do the things that you need to do with async values over time. So time-indexed sequences. Some examples: periodic timers, mouse clicks, mouse moves, network packets, file reads, writes, a stream of trading stock numbers coming through, frames in a video, audio samples. Especially for those last two, it becomes pretty obvious that time isn't necessarily now. Time is a virtual concept that you need to be able to have control over in order for these time index sequences and the algorithms that you use to compose them to provide the value that they really do. And one of the side effects of making time virtual is that when you run your tests on these time-dependent algorithms, they don't take the time that you specified. They can compact all of the events and no longer be lazy and just virtually skip to the next time that they have something to do. And so your tests run very quickly. This is the way we tend to describe each sequence in the Rx community. It's called a marble diagram. It shows how you can have individual things coming in serially over time, and then the straight line is the successful termination, and that's actually an event in the stream. You're done. And then you can have some sort of operator. In this case, it's just turning each marble upside down visually. And your output stream goes until it either completes because the input stream completed, or it failed. And these are your two terminating events that are actually in the stream. One thing this graph doesn't tend to represent is the final termination condition, which is essentially cancel. When you say, even though my input isn't done, I really don't care about the output anymore, just stop. So there's 3 ways to stop. So this is an example of a diagram that shows how you would take an array, pass it to something called from, and what it would do is it would just iterate over the elements of the array and then complete. And that's how you would represent that in a marble diagram. You can do the same thing for range. In this case, it's a generator of integers, and so you're going from n to m as the function call that you make, but what comes out is this stream of values again as fast as it can produce them up until it gets to the termination condition. And you've got interval, and now you've got some gaps being introduced. So you call interval with a delay value, and suddenly these integers come out in an increment, but separated in the stream by the delay. Each of them has a period of delay between when they arrive. And then that one doesn't end. So the only way you're going to stop an interval is by using that cancellation. This is a really cool site called RX Marbles that's pretty recently come up. It has interactive diagrams. You move those marbles around, and the outputs move according to what the merge operator would do with those marbles. And so you've got 2 streams going in this case, and you've got your output stream, and it's pretty cool to just go and play around and figure out how some of these operators work, algorithms. So this is actually native code, and not very interesting, just sitting in the middle of the screen. Here's an example of running the tests. The tests are running up there every draw call, as fast as it can go. But they're testing a full second of values for some functions that we'll see soon. And so the virtual time means that I don't have to wait for a full second to test what the values will be from these functions over a second. I can start orbiting the circle. So now the circle is actually being driven by time. As the time events come in, I calculate around a particular position. I can change my source. It was window center. Now it's all movement, and now the thing starts following my mouse. I have, this is Open Frameworks. And in Open Frameworks, I've built some adaptations. You can essentially adapt any of these things, like I did STL this week to do the Inscription one. You can adapt any of these things to use rxcpp with them. So that's going to be a challenge. So that didn't do what I asked it. Well, it may have done what I asked it, what I wanted it to do. Can I show this? So what we're seeing here are the green lines are actually time updates coming through that stream. And if you open a stream, you can see all of the operators that are involved in that stream. And you can see time coming through. And then when I start moving the mouse, some of the other marbles, operators will start seeing marbles for the mouse moves. All right, let's go back. Whoops. There it is. All right. So this is the type of code that you would write in order to use rxcpp. You have something in that I built that's connected to Open Frameworks that creates a stream out of the update calls, where you would update the state of your object before each draw. And that produces an observable stream of millisecond values that represent the current time at this update. And then you can convert the stream, each of those millisecond values, to a float from 1 to 0, 0 to 1, that represents a period of time, like from 1 second to 2 seconds. It's a 1 second period of time where the value that comes out of this will shift from 0.0 to 1.0. And then it will go back to 0 and go to 1.0. And then this uses sine and cosine to take that 0 to 1 and turn it into a point, which creates that circle that the circle was orbiting around the current point on the screen. So that's the composition there. And then, so that composition is based on time, right? These millisecond updates. And then this composition is based on mouse moves. And we just extract the point from each mouse move. So now I have 2 streams, each of which produces points. And the points from one stream are relative, the orbit stream, and the points of the other are absolute, where the mouse is on the screen. So then I just add them together. Each time either one of those gets updated, that's what combine latest does, sum the 2 values, and then make that the center of the circle I'm going to draw. And that's really it. I mean, we'll go and see that the function that's taking a millisecond value and producing the float from 0 to 1 is just taking each value and mapping it with a period, which is defaulting to 1 second. So every second, this will go from 0 to 1. And it will produce a new value every time we get a new tick, which is on the update clock of Open Frameworks. This function just takes in that stream that was produced by the previous function of values from 0 to 1, and it produces points. And it does that by taking the float from 0 to 1 and calling sine and cosine. That's all it does. So, reactive extensions. This is a library that Microsoft produced for .NET. It followed LINQ. It had the same mathematical underpinnings, but is an inversion. So LINQ was a set of algorithms for IEnumerable. That's the representation that they used instead of iterators in .NET. And so it's equivalent to ranges in C++. And they used names from SQL syntax. So you'll see a where clause in LINQ or a select operator in LINQ and you're able to operate on things that are right there available to you, like lists and all that stuff. Rx inverted it. So in an enumerator, you could get a new enumerator, an independent enumeration of the underlying sequence, and move next to process through it. Whereas in Rx, you would subscribe once to say, I have someone new who's interested in all the values you're going to produce from now on. They both dispose. They both can be canceled. I'm done. Don't want any more. They both can be completed. Up there, it just returns false from move next. Down here, you get a function callback on complete. The current value is either passed into on next or returned from current. And then on error is a throw from trying to access current in the enumerator. But here, it's another function call. And so it's just a straight inversion from pull, I want the next thing, I want the current thing, to push, I want to know about these things, tell me whenever there's a new one. Time is a big deal. So there's a scheduler object, and it owns the concept of now. So when you provide to an operator a scheduler, that operator will use that version of now to decide what time it is. It won't go around trying to figure out what real now is. And that's what enables all of the virtual time, because you can supply a scheduler to the operators that will tell it that time is moving at a rather irregular pace, if you like. And then you can schedule something in that time namespace, essentially, scope. And you can dispose any of the things you schedule, and then you can, that actually is the thing that was going to be run. So the contract is that on next, on error, and on completed are always serialized, meaning you will never get an overlapped call, so you don't have to worry about it. Your code can be very simple. You don't have to have locks. You don't have to have atomics. You're going to get straight calls. Dispose, on error, and on complete, any of those three is what stops the stream, which means that after any one of those occurs, there will be no other calls to any of the methods. So you don't have to worry about, once you've gotten an on error or an on complete, there won't be any more on next calls or on error calls or on complete calls. Don't have to worry about it. On error and on complete call dispose. So dispose is kind of your finally. You know that the lifetime, the scope of this operation is now done. Oops. And there's the diagram again, just to kind of connect it back. This is how Rx implemented this diagram, represented it. So each one of the dotted lines is a call to on next. Unless it's an X, then it's an on error, and the line, black line, is on completed. So rxcpp, it's on GitHub. It's building for Windows, Linux, OS X. It's on NuGet. It started as a prototype written by Aaron Lehman at Microsoft. I went in and made a lot of additions to the prototype, and then peeled it back and started over with V2 to change some of the trade-offs and clean up the surface, what you actually see as a programmer. There's been a lot of movement in RxJava, and so I've been trying to kind of track that too. Whoops. So it's header only, compile time polymorphism, which means things in the chain of operators try to stay static unless you ask for them to be virtual explicitly. Opt-in polymorphism, all of the operators are much like vector or something else. They expect all of the input streams to be from the same thread, like, say, the main thread of a UI application or something. But you can just specify a coordinator, and that will make any particular operator accept multiple threads from multiple threads, input sources from multiple threads. And coordinate them for you. So coordination is kind of outside of the operators, which simplifies their implementation. Sorry, yeah, that's opt-in concurrency. There were a lot of shared pointers visible in the original one, and so this is all ref classes when necessary to keep the shared pointer inside hidden, so you just see dots everywhere instead of arrows. You don't see shared pointers. It compiles GCC, Clang, and VC, and the C++ library is the only dependency, the standard library, not using anything else. So in this, lifetime is controlled by a subscription. You can ask it if it's subscribed, or you can tell it to unsubscribe. You can add nested lifetimes or remove them. The observable is the core of the objects, and this is how you create one. You pass in a function that takes a subscriber, and you call the methods on that subscriber, things like onNext and onCompleted and onError. And so that implements an observable. What gets returned is something that you can subscribe to. And every time a subscription occurs, this function gets called. So anything that gets subscribed to it causes a call to the function you supplied, passing in the person who's interested, the subscriber that's interested. And you just do whatever you were going to do to feed your data into that subscriber. Other ways to create that are built in are from. That just takes all of the values that you put in the variadic template, and like from did in the Marble, it just sends them out as fast as it can to any subscribers that subscribe. Iterate takes any collection that has begin end, does the same thing. The range takes in any integral from first to last with a step, and makes calls to onNext for each of the integral values. Interval does the time from an initial and for a period. So it'll start the initial one, and then from that point, every period a new value will come out. You can have never, which will never call anything on any subscriber you pass to it. So the only way to get out of it is to call the unsubscribe. And you can call empty, which will immediately call onCompleted. And you can call error, which will immediately call onError. So there's these different, all of the ways of just kind of sending one thing, you just pass one to from, it sends one thing, it completes. Sending an error immediately because you're telling your caller that it needs to stop. Just some easy ways to construct an observable. Once you have an observable, the primary thing you do is subscribe. And when you subscribe, all of these parameters are optional. So if you just call subscribe, it will create a lifetime internally for the subscription, and it will ignore any values that were passed on next. And if onError is ever called, it will crash the process. It will exit. So if you don't want that behavior, then you need to supply onError at least. Filter is one of the, so in order to make this work well with IntelliSense, all of the operators are in the observable class. And so that you can just dot and then get a list and pick the algorithm you want. So filter will do what would do essentially what copyIf does. And map essentially does what transform does. Flat map lets you have, for every value that's coming in, produce a whole series of values coming out, and then merge all of those produced values together into one stream. So you still have one output stream, but now if you had states coming in, you could have cities coming out, and you'd have a huge stream of all the cities from all of the input states as one stream. So it's kind of a collapser. It's a way to collapse nested data structures into a single stream. Combine latest, we already saw. whenever any of its inputs updates, a new value comes out that's a tuple of all of them. So it's remembering the most recent value it got from all the streams so that it can produce the new tuple with the old values. Merge is embedded in FlatMap, but this just takes them without the flattening part. This is without flattening. So you just take, if you had already gotten a separate observable for for all the cities from each state, then you could pass them all into merge and you'd get all the cities from each state the same way. Concat would make sure that you got all the cities from one state before you got any of the cities from the next state. So it only subscribes to one thing at a time, but it still ends up pushing them all out the same output. Right. So some of these are fairly simple transformations, like the same type of value that goes in comes out because you're just filtering. Some of them are different types. So you're coming from one type and converting it to another type. Coordination, this is how we introduce thread safety when needed. By default, we're going to be using either identity immediate or identity current thread in the operators. And so we don't do any coordination, and anything that you schedule from a time perspective either is scheduled on the current thread scheduler or the immediate thread scheduler, respectively. Immediate doesn't schedule at all. There's no queue. It just immediately runs. So you can blow your stack with immediate if you're not careful. And current thread implements essentially a trampoline or a derecursor. So it queues up things and keeps on winding back from each one before running the next one. So you can't blow your stack. A little bit of overhead, though. An event loop just starts up a few threads to distribute things between. It's very simple, like round-robin scheduling, nothing crazy. And the new thread gets a new thread every time you want to use a coordination. So there's no limit on the number of threads you can create. You have to be a little bit careful with that one. Those two are also serialization ones. They use a mutex when they're coordinating. So that means that your output stream will actually be getting on next calls from multiple threads, but they will never overlap. On the other hand, this observe-on version actually uses a queue, and there's only one thread that's ever going to call out of the output of this operator. And all of the input threads, the values actually got pushed onto a queue and then popped off on this other thread. So you're actually conveying objects through to a single output thread. And there's an example of the suggestions you get in an IDE when you do a dot on a stream. Yeah, I already did that. Okay. So this is a test. You make a test scheduler that represents virtual time, and you build a set of messages that you want to convey from that scheduler and the times you want them conveyed. So the first number in each of those on next calls is the time that this value is supposed to appear. And then on the right side is the value that's supposed to be sent at that time. And so once you've done that, you can start the scheduling of those items, and it will, instead of waiting, 100 milliseconds or however you want to interpret the values on the first column, it will actually just loop through those as fast as it can and call on next and on completed. So in this case, we're passing it to the function we looked at earlier that's mapping millisecond times into a float from 0 to 1. And so we just now create another vector of the same, it's not the same type because the output type is a float instead of the input type being an unsigned long. But you put the values into it that you expect to come out of the function for those input times that you put in above. and then you get the actual messages that were recorded here from start, the return value of start, stored of everything that was sent out during the start call. And once you've got that, you can actually compare required to actual and figure out whether or not you succeeded, and that's your test, whether the output it matched what you expected. So this is the same thing, but it's for the second transformation, where we're going from floats from 0 to 1 to the points. So those are the same input. These inputs are the same as the outputs from the previous one, and then those outputs are the points that we expected to come out for those input values. So unit tests, I'm using the catch library, which I can't help but highly recommend. I picked it, and one of the best things about it is, you see you're building the test the same way with the same components. You'll notice that I intentionally didn't do the take that all of the text strings say I did. I did a skip. So this isn't going to match the input. I didn't get the output I expected. So this require macro, I'm getting the actual messages. This require macro uses expression templates. And so what you get out of it is actually a list of each of the things that you passed in with the time and the value. And you can just compare and see how you were different, not just that you were different on failures. So now we'll introduce some concurrency. Have to bear with me, it's got to be smaller. On this one. Nope. That's not helpful. Thank goodness. All right. So when I click Start Image, it's going to start scheduling URLs to come out of a stream every 200 milliseconds, 20 of them, the same URL over and over again. And you'll notice that the result was not only that we downloaded everything and rendered it, but some of these say that they got through 100%, and some of them say they got through less than 100%. And that's because we have two different scheduling policies involved here. In one of them, while it was downloading something, another URL came in. These 200 millisecond delays meant it came in later. And we're round-robin scheduling. But anyhow, it came in later. The behavior of these are when a new URL comes in, stop whatever you were doing and switch to the new URL. The behavior of these is wait and do the new URL after you finish the current one. And so you can see that you got the different behavior from these things. But the code to do that is just, here's my the button on the UI, and I'm going to map it to send those URLs. I'm going to merge all of the images coming out, all the URLs coming out, because I can click the button multiple times, and each of them will produce 20 URLs over time. So this merge puts all of the URLs from all of the button clicks into one stream. And then as each URL comes in, I'm going to group them into a thread count. So I don't want any more than 8 threads processing these URLs. So that's what thread count is. It's a number. And so for each of the URLs, I group it into onto a particular thread. So the URLs are getting distributed across these 8 groups. I have 8 new URL grouped observables that exist. Only 8 ever. because of this key that I'm returning from group by. Always goes from 0 to 8 or 7. And so for each of those that I get, I'm going to create one thread for that particular group, and then I'm going to go get images on that thread. And then all those images I get, I'm going to merge together and subscribe to it. And that's the whole thing, except for some of the function calls that are being made. So to get to the point, this is the difference between those two execution policies. Switch on next aborts whatever it's doing when it gets a new item on the input. And concat stores whatever new items it gets on input and does them when the previous one's complete. So that one line change changes the policy. And then we update UI. The other thing I can show here is this lift operator. I wanted to be able to filter out the errors and display them in the UI instead of destroying my whole stream. So I actually built a new operator that isn't in Observable, and it's this lambda. And this lambda is an operator. All it has to do to be an operator is to take a subscriber and return a subscriber. And then you use the lift method on the observable, and you can insert any operator you want. And it can, in this case, error display will implement on error to display the error in the UI instead of unwinding the whole subscription. And then retry means that after one of those errors occurs, we'll retry over and over again until we succeed. And we can also cancel. So take until takes another stream from another button on the UI, and when I click that button on the UI, it gets passed to this stop stream, and that causes take until to dispose of the whole chain. Yeah, I don't think we care about this. Yeah, that's the end of the code. I'd like to spend the rest of the time taking questions from people about, like, why would you, did I not motivate, why we would need these types of algorithms available, or questions about the specific representation or implementation. Yeah, I'm here. Please ask.
What are some of the practical applications?
So if you look on the web, you'll find trying to figure out the best way to say this. There's an application, open source application called Reactive Trader that is written in .NET and JavaScript. The same thing as a demonstration. And this is used as it's a open source version of an actual app that this company produces that allows traders to see real-time information coming in very quickly in a dynamic UI. So you've got that usage. Netflix uses reactive extensions for Java and JavaScript for both its player implementations and its server implementations. So a good portion of what's going on in producing Netflix is Rx-based, but in the Java language and the JavaScript language. GitHub for Windows, the Windows UI is written in Rx.NET. And the GitHub for Mac OS client is written in Reactive Cocoa. So there's a lot of UI applications, and then there's also a lot of server applications. One of the things that Netflix really liked about reactive extensions is that they could actually have their engineers kind of flipping back and forth between server and client and knowing how the frameworks worked, because it was just Rx and this pattern and this way of thinking. Yes?
How hard is it to create your own subscription? Or like what are the necessary things that need to get implemented? What are the...
So make subscriber.
Sure.
Yes. Okay. How do you create a subscription? How hard is that? A subscription is very easy to create. You can call a make subscription static function and pass in any of the same. Let me rewind a bit. So when I showed subscribe on observable, the subscribe method took optional parameters, including lifetime, on next, on complete, and on error. What subscribe actually does is it calls this static function make subscriber. So the subscribe function is just a forwarding function to make subscriber, and make subscriber takes all those same optional arguments. So you have the option of passing in a lifetime. If you want to chain multiple things to the same lifetime, you can do that by passing the same lifetime into multiple subscriptions. And then, but it's optional, otherwise one will just be created for you. And then you have to have, you don't have to, but if you want to know what the values are that are coming out of this, you should apply a lambda or a function that takes the value type. And so that function will then get called for each. It implements on next, essentially. Your lambda becomes the implementation of on next. And then your lambda for the on error parameter takes, whenever there's an on error call, it will call your lambda, and so on. So implementing a subscriber is just calling subscribe with some lambdas.
I meant a subscription class. The question I have then becomes, how do you control weighting? Like, weightings are like OS events, or is everything getting chained back on nets?
So subscriptions are asynchronous. So when you call, well, potentially, depending on your input source. So everything is very dependent. If your input source is a mouse event, then what you've essentially done is you've created a subject observable pair called a subject, and you've subscribed for the mouse event, and every time a mouse event comes in, you call on next on the subscriber side of the subject, and anyone who subscribes to the observable end of the subject will then see that any on next that were passed in from the UI. So then your source is actually the UI thread calling through to your on next. So your call is actually on the UI thread in that case until you insert like an observe on or something that moves it to another thread. Did that answer the question?
I'll
Okay.
try and reword it later.
Okay.
So my question is about the way virtual time is sort of built into this framework. So I'm curious why that is, because it seems like many applications of this won't really care about time in terms of numbers. They're just handling events as fast as they come in, and it also seems like it weighs against one of the things that seems to come up a lot when you're dealing with concurrency and things like that is that you can't necessarily think of the world as a linear sequence of events ordered in time. That different threads, different CPUs may observe events in different orders or have an undefined order, all that kind of thing. Mm-hmm. And it seems like the virtual time could be a separate component independent of the framework. Can you comment on why that wasn't done?
So the virtual time is required to be integrated into the operators because some of them actually take values of time as parameters. And you can imagine using that for buffering. I want to buffer 20 milliseconds of data at a time, mm-hmm. and I want the output to be vectors of the last 20 milliseconds. And every millisecond, I want to start a new buffer, essentially. So you're going to get these situations where when I'm testing that operator functions, I don't actually want to have to wait milliseconds to figure out whether it works.
Right, but why not, rather than have the time be supplied by the framework, why not have the individual operators be parameterized by a time source
And they are.
off to the side?
That's what the coordination is, and the scheduler. So the coordination has a scheduler, and the scheduler has a time. And when you need to change an operator's concept of time, you pass in a coordination. When you need to change the way that it coordinates between the input streams, like for a merge of multiple streams, then you pass in a coordination, but it's optional. The default one is going to use real time, the steady clock.
Okay. Okay, thank you.
Go ahead.
Can you maybe explain, I'm just wondering, let's say if I have a single-threaded application, right? I think it was one of your test examples where you were defining a sequence of numbers, and then one end produces the sequence of numbers, and in the middle you have some sort of timer which slows down this producer and produces numbers with certain intervals of time.
Mhm.
So how this slowdown is done? I mean, are you actually somehow unwinding the entire call stack, or you have to actually sit there and sleep for some period of time, and that's what slows down producer?
It depends on the scheduler. Oh, yeah. So when you have an operator that is slowing down an input sequence, I forgot how you phrased the question.
I mean, how do you, well, a simple way to ask is, how do you slow down producer?
Yeah, it's called back pressure. It's actively being discussed. There is an attempted implementation in RxJava right now. rxcpp doesn't have back pressure, so one of the things that you have to manage is if you have fast producers that are faster than your consumers, you have to decide what your policy is, and usually the most natural policy is to scan, essentially, which is one of the operators, which means I am going to ignore most of the values that are coming in so that I can, or I'm going to aggregate them in some way so that I can keep my consumer up to speed with my producer.
But you cannot unwind the thread. You pretty much are holding thread while you are, I'm sorry, if I want to sleep, if I actually want to wait, if I want to inject time intervals and then want to skip anything, then I either have to cache, buffer it, and then issue with interval of time, or you have to do the sleeps on the thread. There's two options.
So do I have to repeat the question, how do I decide whether I'm going to sleep in an operator or in order to wait for something and block the thread, or unwind the thread and come back later? And that is a function of your scheduler and your input source. So if you schedule something to happen in the future, the scheduler you use will determine whether or not it's current thread and sleeps the current thread, or immediate, which sleeps the current thread, or like new thread would actually start up the new thread and ask it to sleep and unwind the original one. Or
So it's my understanding that this doesn't really make a ton of sense unless you're running some sort of event loop architecture. Is that correct?
no, I mean, the servers at Netflix don't run an event loop architecture. There's a sense in which you can consider the current thread scheduler an event loop, but you don't ever have to schedule on it if you don't want to. So you can create a new thread and have your scheduler working within that new thread, or you can create a thread pool scheduler and have it just distributing all of the work across all the threads in the thread pool.
Yeah, I understand, but it seemed like in the trampoline example that you gave, you can't exactly unwind the stack in the manner you proposed unless you have some sort of thing that's calling in, like an event loop. Maybe it's called something else in the reactive frameworks. I'm not familiar, but
Well, if I have-
similar question to what he had is that you can't
Okay.
just sleep your thread. Like something has to come back and call you.
Well, the way that these schedulers work is they keep a queue that's a heap, priority heap. And so the priority is the time that this event is scheduled to occur. So it's never going to sleep. It's always going to pick the thing that's that needs to happen next to be the thing that it sleeps for.
Yeah. So that's my understanding of an event loop for the most part.
I see.
Yeah, okay, sorry.
Each thread would be an event loop, but the way you deal with the more dynamic input that I think you're hoping for is by having multiple threads. Mhm.
I'm not sure if you thought about this, but I just cannot help thinking, if you have something like coroutines in the form of await and yield,
Yes.
then you could oftentimes build a similar chains of consuming pipeline using coroutines.
Mhm.
So what are your thoughts? Which one you like?
I consider the coroutine, yes. Isn't this just something that coroutines could replace? I consider coroutine a representation. And as I was hoping to communicate, the representation, as long as it provides the properties, is irrelevant as long as I get the algorithms. That's what I care about. I don't want to have to write merges manually. I want them as an algorithm on whatever representation exists. So there are properties that you have to make sure are in the coroutine. You have to be able to get errors. You have to be able to get a completion notification. And you have to be able to get a final notification of lifetime termination, right? And if you can get all of those things and yield out values, then yeah, you've got what you need in order to then go and get your virtual time and build a whole bunch of operators outside of that. I think that's all I have. If there's no more questions.